Okay, we're going to go ahead and shift gears here and talk about the idea of average rates. Now, you might be familiar with that term, average rates. The idea of average rates is if you're driving in your car, let's say, and you're traveling from wherever you're at, you're traveling at house and you're going from your house to Disneyland. And so you get on the freeway and you calculate how many miles you drove, and you look at your watch when you got to Disneyland. You figure out that it took you 2 hours to get there, and you drove a total of 100 miles. How fast were you going? Well, that's simple. Distance equals rate times time. You just divide. You take the distance that you traveled and divide it by the time, you get your rate. Okay, well, if I traveled 100 miles in 2 hours, that means I was driving 50 miles per hour. Well, not really. You weren't traveling 50 miles per hour throughout the entire journey. When you got in your car and you started driving away, you weren't driving 50 miles an hour at the moment you drove away from your driveway. You were slowly speeding up, and then slowing down, speeding up at stoplights and whatnot. You get on the freeway, you speed up. Maybe there's times within the trip on the freeway that you're going 45 miles an hour because of traffic, and then maybe you're going 65 miles an hour or 70 miles an hour on the way there. The 50 miles an hour that we're talking about, the 100 miles divided by 2 hours, is your average rate. It's not how fast you were going throughout the entire trip, because your rate changes. So that's kind of important, right? Average rate is the overall number that represents how fast you were going overall on average, okay? And the way we do that is we figure out the distance that was covered, 100 miles in our case, and divide it by the time that we were traveling, which in our case was 2 hours, okay? So here's an example of this. At t equals 3 minutes, a ball is 50 feet away from a wall. So here's a wall, right? There's the wall. At t equals 3, the ball is 50 feet away from the wall. At t equals 7 seconds, the ball is, what does it say? 100 feet away from the wall, okay? All right, there's that, right? Now this isn't a function. I haven't drawn a function out. We can create a function. The function would be, well, we have a coordinate of 3, 50 and another coordinate of 7, 100. And so we can graph that, and we can say, okay, well, 3, 50 is here, and then 7, 100 is there. And so we have this relationship on average linear function in a sense. But what is the average rate? Well, the average rate is actually just the slope. It's just the slope of the function over 2 points. So we would say the average rate is equal to y2 minus y1 over x2 minus x1. It's our slope. That's all it is. So we end up with 100 minus 50 over 7 minus 3. And again, what does this mean? Well, it means that the ball traveled 50 feet over 4 seconds of time. 50 feet over 4 seconds of time. So our average rates, what would that be? 25 over 2, so that'd be 12.5. And then we always include units whenever we can. It'd be 12.5 what? Feet per minute. Feet per minute, because it's a rate. Okay, and that's exactly this. What is 100 minus 50? Well, these are feet, and what's the 7 minus 3? That was time, that was minutes. And so it's 50 over 4 feet per minute. And that's our average rate. Pretty simple, pretty straightforward, I think. Okay, and we can see it like that, 12.5 feet per minute. Now let's go ahead and take a look at a little bit more lengthier of a word problem here, but looking still for the same thing. An object dropped from rest falls such that its distance traveled over time is d of t equals 16t squared. And that should be recognizable. 16t squared, 16 is the force of gravity. You would put negative 16 because it's falling. but we're not interested in the direction right now. It says, what is the average speed of an object over the first 2 seconds? And so we have, whatever, this object that's being dropped off of a cliff maybe, and we're dropping the ball and it's falling. Okay? We want to know how fast it was traveling on average over the first 2 seconds. Well, this represents the position of the object at different times. So what 2 times do we care about? Well, we care about when we started, d of 0, and we care about 2 seconds later, so d of 2. So we just figure those 2 values out, and that is 0. So our position, in a sense, is 0 at time equals 0. In other words, the ball didn't move at all. And then d of 2, well, that'd be 4. 16 times 4 is 64. So 2 seconds later, it had moved 64 feet. Now we're looking for the average speed or the average rate over those 2 seconds. And so we would figure out the change in distance, which would be d of 2 minus d of 0 over the change in time, which is 2 minus 0. Well, how far did it travel? It traveled 64 minus 0. So this is where we ended and this is where we started. So how far apart are those? 64 feet. How much time elapsed? Well, we started at t equals 0 and we went to time t equals 2. And so we end up with 2 there, right? So that's going to end up being 32. And the units on this, because it's a rate, it's going to be something per something. It's feet per, I believe, second again, okay? So the average rate at which this particle is traveling over that time is 32 feet per second. But what you'll notice is, first of all, this is a parabola, and that makes sense because what happens over time? Well, the object is going to speed up, which means it's going to cover more distance as time goes on. And so all we did, and we're going to get more into this into the future, all we did is we found the slope between t equals 0 and t equals 2. We found the slope, in other words, the line here. So we found a rate that, we found the slope of that line, which represents the average rate of that curve. It doesn't match it perfectly at all points because it's curvy versus straight. Okay? So just reiterating that. And then we'll add, you guys go ahead and pause the video and give this one a shot. Same scenario, same equation. Find the average speed from t equals 1 second to t equals 5 seconds. All right, so hopefully you had a chance to work that out on your own. We're working with the same function here. And we are looking for the average speed or the average rate from t equals 1 to t equals 5. So we need these 2 positions, d of 1 and d of 5. So if I plug in 1 here, I end up with 16. If I plug in 5, oops, thinking ahead too much. Let's see, that's going to be 5 squared is 25, 400, I believe that is correct. Okay, we'll check it in a second. And then we're going to find the rate, average rate over that interval from 1 to 5. And so that's going to be 400 minus 16 over 5 minus 1. That's going to be 384 over 4. What is that? 36 is 9. 24 is 6. And so that would be feet per second. And that is our answer for that one. Now, what does that mean? Like I said, this should make sense. This should be clear. We had a parabola here, and in the first case, we found the speed from 0 to 2, and we found that rate. That rate was 32 feet per second. Now, from 1 to 5, we found that rate at that point, and so we drew kind of another tangent line. We can see that this rate is steeper than this, or this line is steeper than that line, so its slope is going to be greater, and in fact it is. 96 is greater than 32. So that is the idea of the average rate. How do you find average rate? You take 2 coordinates, 2 positions, and do the slope on those 2 positions. The change in distance over the change in time. To do that, you need 2 points. Now, let's go into this idea of instantaneous rates. Well, instantaneous rate is the speed or the rate of an object at a specific moment in time. And so the only way, like if you're driving in your car going to Disneyland, the only way that you can get an instantaneous rate in that context is to look at your speedometer, and it tells you how fast you're going at that moment. And really that's the big question that we're concerned with, is not what the average speed is, but what the instantaneous speed or the instantaneous rate is, okay? Now, something that you might cross your mind a little bit, how do we find rate? Well, we take the two positions that we have and we plug it into the slope formula, essentially. That's how we find the speed of something. We need two positions so we can figure out the change in position. We need 2 times so we can figure out the change in time. When we're talking about instantaneous speed, we're talking about how fast you're going at this moment. So how many points of data do you have? You only have 1. So how do you apply the slope formula to 1 point? That's the question, and that's really the question of calculus, okay? So the instantaneous rates can use the idea of limits to get to our goal. And what do I mean by that? Well, we're going to get more into this. So if this is a little overwhelming right now, we're going to spend more and more time on this. Now I'm going to rewrite this down. The rate of something, remember, the rate of something is equal to the change in the distance over the change in the time. Well, how did we figure that out? We figured out the distance at the second point of time, so t2, minus the distance at the first point in time over the second time minus the first time. That's how we do it. We need 2 points to do that. But if we only have 1 point, this is where limits come into play. Okay? If we only have 1 point, how could we do this? Well, we would write it like this. We would say that the instantaneous rate, rate is equal to the limit, okay, the limit as h approaches 0 of d of t plus h minus d of t over t plus h minus t. And you go, what? What is that? We're going to spend a lot of time on this actual idea. And basically, here's what it comes down to. Normally, here's my curve. If I want to find the average rate, this is average rate. Let me go ahead and write this down. This is average rate. Okay. If I want to find the average rate, I take my first time, time 1, and my second time, time 2, and I evaluate those points. So this right here is d of t1, and then this is d of t2. So you can see that the coordinate is t1 comma d of t1 and t2 comma d of t2. Okay, and then we'd plug those into the slope formula. Okay, so that's what we were looking for here. We were looking for the average rate. Now that let me be a little bit more extreme. Let's say that this is t2 and that this is the point up here, d of t2. Okay, that way our points are a little bit further apart from each other. Maybe we can see. So you can see that it's not the actual curve, it's just the slope of that line. What we want maybe though is this. What we want is the slope at t1, and essentially what we're doing is we're finding what's called the slope of the tangent line, the line that just skims the curve. Well, what we're going to do is we're going to represent t2 in a different way. Instead of saying t2 is t2, we're going to write this. We're going to say t2 is equal to t1 plus h. So the distance between these 2 points is h. So instead of using the idea of 2 different points, we're going to rewrite the second point in terms of the first point. Well, how do I get to this second point? I take the first point and I add how far apart those 2 points are. Okay? Again, don't let this be overwhelming for you. We'll get more into it in the future. Make sure you're asking questions as time goes on. But notice this instantaneous rate equation, it's the limit as h is approaching 0. So what's happening is that this distance here is actually shrinking. So we are taking this t2 and we're moving it closer and closer to t1. And so you can see as it moves closer and closer, h is getting smaller and smaller. Okay, it's getting smaller and smaller. And so now to find this rate, that rate between those 2 points is a lot more accurate to the actual rate at that point than these 2 points are. The idea is that we want this distance to be infinitely small. We want it to be 0 or approaching 0. So what we really want is t2 to be really, 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 really close to t1. And that's why we take the limit as h approaches 0. Well, let's take a look at what that looks like in an example. Okay, so let's say, and maybe this will clarify things a little bit, let's say that t2, so here's t1, t2 is slightly later than t1, so it's just after it, just barely after it, infinitely closely after it. Therefore, we could say t2 is t1 plus a little bit, plus h, where h is really small. Okay, and therefore we can conclude that we have this equation. Okay, d of t1 plus h minus d of t1 over t1 plus h minus t1. And then you can see as a result of that, let me go back. You can see as a result of that, when I simplify the bottom, t1 plus h minus t1 is actually going to cancel out the t1s and you're left with h. And we'll get more into that in the future. But let me show you what this looks like in an example. We'll use the same equation that we did before. These equations don't necessarily have to be the same, but I'm just using the same one to help us out here. Okay, we are looking for the instantaneous speed at t equals 2. So the speed when t equals 2. Well, remember, we need 2 points. We need 2 points. What is the first point? The first point is 2. Okay, so we got to figure that out. What's the second point? Well, we don't have a second point. How did we represent the second point? We took the first point and added h, right? We added a very small amount, a very small distance. So that's point 1 and that's point 2, and h is really small. So let's figure these things out. This would be 16 times 2 squared, which is 64 again. This we're going to plug into t. That's going to say 16 times 2 plus h squared. Okay? Now, I'm going to leave that. In fact, I'm going to leave that both like this just so you can see how this all goes together. And I'll do it 2 different ways so you can see it. Okay, so now if I take the slope here, my slope is going to be 16 times 2 plus h squared minus 16 times 2 squared, okay, over 2 plus h minus 2. There's my slope formula right here. y2 minus y1 over x2 minus x1. y2 minus y1 over x2 minus x1. Now, if I go to simplify all this, you're going to see something. You're going to see that, let's see, I'll simplify that. I'm going to square that binomial. So 4 plus 4h plus h squared. And then oops, minus 64 all over. Well, this simplifies to just h on the bottom. Well, simplifying all this, distribute that. You got 64 plus 64h plus 16h squared minus 64 over h. Okay? Now, we notice that we have a problem because how small was h supposed to be? H was supposed to be really small because remember, these 2 points are supposed to be really close to one another. If h is really small, that means h is getting close to 0. Well, if I plug in a 0 for h, I'm going to have a problem. Because if I plug in a 0 here, that cancels out. If I plug in a 0 there, that cancels out. And if I plug in a 0 there, that's 0. So this turns into 64 minus 64, which is 0 over 0. So we get 0 over 0, which is indeterminate. That's where the idea of limits comes in. Okay? So instead of just looking at this as a slope formula, we're going to write this out. We're going to say we want the limit as h approaches 0. You see, we can't find the rate between one point and itself if h was actually 0, we'd be finding the rate at time 2, time 2, which is the time is 0. That doesn't make sense. So we take the limit, so we say that h is getting really close to it. Okay? And then we simplify it from there. Well, like I said before, this turns into 0 over 0. So we have an indeterminate form. Indeterminate. So what do we do when we have an indeterminate form? Well, we try and factor. Well, in this case, factoring is a little, it's not as apparent. Let's just simplify. 64 minus 64 cancels out. So I'm left with 64h plus 16h squared all over h. And that's the limit as h approaches 0. And then you notice that both of these have an h in there. So I'm going to simplify that. That's the limit as h approaches 0 of h times, I'm going to factor, 64 plus 16h over h. And now we can see, oh, the h is reduced just like they did, just like the factors reduced in the previous problems. So we're left with the limit as h approaches 0 of 64 plus 16h. And now we can just substitute. So we end up with 64 plus 16 times 0, which is 64 feet per second. Okay, I realize that this is a lot of information right now. Don't stress over it. We're going to get lots of practice with this. But I wanted to show you one quick way that might help you see it a little bit. Let me get rid of this. It's essentially the same thing. But what I'm going to do is I'm going to simplify our 2 points first. Okay? So we know that this is 64. And we know that this is going to be, again, I did the work earlier, but it was 16 times 4 plus 4h plus h squared. And then distribute that, you got 64 plus 64h plus 16h squared. Okay? So there are our 2 coordinates. Our 2 coordinates are 2 comma 64 and 2 plus h comma 64 plus 64h plus plus 16h squared. And then we just plug those into the slope formula. So it would be y2, 64 plus 64h plus 16h squared minus y1, so minus 64, all over 2 plus h minus 2. And I'll put parentheses around this just so that we don't mix anything up. And then we'll simplify that from there. 64 minus 64 cancels out. You're left with 64h plus 16h squared all over h. We notice that we have a problem because we're actually taking the limit as h approaches 0. Okay. So when I plug in 0, I get 0 over 0, indeterminate. So I'm going to go ahead and factor it. And this work is all the same now. H times 64 plus 16h over h. Again, those reduce. So we have the limit as h approaches 0 of 64 plus 16h, which is 64 plus 16 times 0, which is 64. All right, and again, feet per second. Okay, so just remember that rate, instantaneous rate, is still the slope formula. It's just that the one point that you have, that's t1, the second point is going to be the original point plus h, or the original time plus h, that's all. Okay, so that's that. And you can see how that works out, where h is really small, or in other words, it's 0. Okay? All right, here's an example or practice problem that I'd like you to try. Instead of when t equals 2, I want you to figure out when t equals 3. So go ahead and pause the video and see how you do. All right, for t equals 3, well, we're gonna kind of go through it step by step. We need to know the position at t equals 3, so we're going to plug that in. So that's 90, 54 is 144. Okay, so that's simplified. The next point we need, because we're looking at when t equals 3, not an average rate, we're looking when t equals 3, so we're going to say 3 plus h. So that's going to be 16 times 3 plus h squared. And then that simplifies to 16 times 9 plus 6h plus h squared, just distributing the binomial there. 16 times 9 is 144, plus 16 times 6 is 96h, plus 16h squared. So those are our two coordinates. D of 3 is 144. D of 3 plus h is 144 plus 96h plus 16h squared. And then we're going to plug those into the slope formula. So it'll be 144 plus 96h plus 16h squared minus 144 all over 3 plus h minus 3. And we're taking the limit as h approaches 0. We'll simplify this. The 144 minus 144 cancel out. And then the 3 minus 3 cancel out. And so that makes it look a lot easier. If I plug in 0 here now, I get 0 over 0, which is indeterminate. So I'm going to try factoring. So I'll factor out an h. And I could factor out other things, but there's no need, because the issue that I have a problem with is the h. So I'm just going to factor out the h if I can. The h's reduce. And so you're left with the limit as h approaches 0 of 96 plus 16 times 0, which is 96 feet per second. So the particle was traveling 96 feet per second when t equals 3. And going back real fast, when t equals 2, the rate was 64 feet per second. And that makes sense. As time goes on, the object is going to get faster and faster and faster. So when t equals 2, it's going that speed. When t equals 3, it's going that speed. So it's going faster as time goes on. Okay. All right. So going back over that, you can see the same kind of work there. I'm going to go ahead and go on to this last part. The main purpose of this lesson was to talk about limits. And the last couple slides we're talking about the application, or one application of limits. So don't stress so much if you didn't get that second part of it. The real focus is on the first part, how to determine limits. And what did we talk about? We talked about the first step is to try substituting. The second step is to try, if substitution doesn't work, you get indeterminate form, then you can try factoring or something like that, and then reducing. But this exit problem here, we're looking for the limit as x approaches 0 of sine of x over x. Let's go ahead and try substitution. So we end up with sine of 0 over 0. Well, what's sine of 0? Sine of 0 is 0 over 0. Uh-oh. We have, what is that called again? That's called indeterminates. Indeterminate. Got to spell it right. Okay. That's an indeterminate form. So what do you try doing? We try factoring. That's the only thing we learn. We're going to learn more things in the future. But we try factoring. Well, there's nothing to factor. Sine of x? No. Maybe I can rewrite it using some trig identity or something else, but I don't want to go there, and that's not going to work anyways. So what do I do now? I can't factor. Well, the only thing left to do is to just kind of get an idea based on a table. Remember, we did that a few slides ago. So let's go ahead and create a table. We're going to talk about from the left and from the right. Okay? So an x, we'll just call it f of x. We'll name the function f of x. Now what values do we use? We're trying to figure out as x approaches 0. So maybe we'll start with -1 from the left, and then we'll go to -0.5, and then -0.1, and then -0.01, right? And maybe -0.001. Okay. From the right, what values would we pick? Well, maybe we'll start at 1, and we'll just do the opposite. 0.5, 0.1, 0.01, 0.001. Okay. So remember, we're going to use our calculator to figure this out. So in your y list, you're going to type in the function. So it's going to be sine of x divided by x. And when you hit enter to put it in the y list, make sure it looks like what it's supposed to look like. You're going to go to we already have our table set to say ask. So we're just going to go to the table. Remember, green F5, and start plugging in these x values in. So at -1, we've got point. What do we got going on here? Something. Oh boy, we got a. let's see, negative 0.5. What is going on here? Negative 0.1. They're all giving me the same values. Oh, you know what? Haha. Make sure that your calculator is in radians. So to do that, you're going to hit mode and scroll down to where it says angle and make sure that says radians. That's my fault. So on negative 1, we have 0.841. We'll round to the nearest thousandth. On negative 0.5, we got 0.959. Negative 0.1, we have 0.998. Negative 0.01, we have 0.99998. And the last one, negative 0.001. Now, depending on how you look at this, your calculator just probably popped up the number 1. That's because it didn't want to show all the digits. But if you actually scroll over to where it says 1, it shows you more accurately what it is. 0.9999, a lot of nines. 1, 2, 3, 4, 5, 6 nines. 8. Why not? Okay. Then we do the same thing on the other side. So we're going to plug in 1 and 0.5 and 0.1 and 0.01 and 0.001. All right, so we got 0.841, 0.959, 0.998, 0.99998, and then the last one is going to be the same thing again, 0.999, da la la la. Okay? So the idea is what? What do we see? As x approaches 0, from the left, we see that it's approaching the value of 1. As x approaches 0 from the right, we see that it's approaching 1. And so as a result of this, we can say the limit as x approaches 0, sine of x over x is 1. Now, we're not going to be able to prove that analytically at any point soon. We'll deal with that later in future lessons. But for now, it's going to be very important that when you do your homework assignments and other things in the next few days, that this one is memorized. You just need to understand that the limit as x approaches 0, sine of x over x is 1. If it was the limit as x approaches like 1 of sine of x over x, it's not going to be 1. You just plug in 1. But this one's unique. The limit as x approaches 0, sine of x over x is 1. Put that in your memory bank, memorize it, and know it, and then we'll prove it in a future lesson. All right, that wraps up the lesson for today. I realize that this was actually a pretty long lesson, but hopefully future ones won't last as long. Hopefully you got something out of it, especially when it comes to limits and substitution. If you have any questions, make sure you're emailing me, logging into the Zoom meetings, asking. Do not be shy about asking. Guys, this is, it's so important that when you're trying to learn through video, that you are not silent about your education. You have to be seeking help when you need it. But anyways, I will talk to you again in the future and in the next video. See you around.